Organizers for inviting me here. It's always a pleasure to be here. I'm going to talk about the program of classification of differential difference equations. And let me first, so I plan to do it fully there, but then decided to add first this bit. So what we are going to study is equations of the form ut equals some function, polynomial or formal series of up, etc., uq, where u will be two different things. So we will have two different considerations. Either we will consider u to be just a function of one discrete variable n and one continuous variable t, and in z, and by un we denote u of n t, or u un will be matrix of arbitrary size n, which depends on, again, discrete variable n and continuous variable t. So these are differential difference equations, one variable continuous t, one variable discrete, and the second case is the most interesting. So that's what I'm going to talk about mostly, the non-abelian equation. So we may assume that for simplicity, you may assume for simplicity that our variables leave matrices of arbitrary size. So if they're arbitrary size, we have no relations. However, well, if you fix the size, then obviously we have the relations with, for instance, we have Hamilton-Carey. By integrability, we will understand the existence of infinite hierarchy of symmetries. And it was noticed long before, well, at the very beginning of integrability, when integrability started, that all these structures, symmetries, conservation laws, Lax representations, etc., do not depend on, in the non-abelian case, on matrix elements explicitly. All what we need is that the equation, variables in the equation, live on some non-abelian associative algebra. So let me first start with some examples of integrable equations, non-abelian integrable equations. So the most simple and the most famous one, which was written already by Peter Lax, is the non-abelian Korteweg-de Vries equation. Then, well, these are other examples. So two versions of the modified KdV equation. Yeah, commutator here is the usual commutator of variables. So uxx minus uxxu. Well, this is the non-abelian Burgers equation. By the way, there are two different versions of it. So this is one of them. You can interchange ux and u. Well, other famous classification results. So first of all, Olver and Sokolov wrote quite a few examples of such equations, Hamiltonian structures, etc. Then Mikhailov and Sokolov set the theory for non-abelian ODEs, and then Olver and Jinping Wong classified scalar homogeneous non-abelian PDEs of arbitrary order. Homogeneous, I don't want to explain what this means, but so in other words, at all orders. So they have shown that only the KdV type equations actually survive. There are no Savada, Katara, Kauf, Cooper-Schmidt non-abelian versions. And recently, Adler and Sokolov classified nonlinear Schrödinger type equations of well, non-abelian nonlinear Schrödinger type equations, and Sokolov and other authors started the classification of non-abelian Penlevet type equations. Well, in the differential difference case, the situation is much worse. So the differential difference equations did not enjoy such such a study. So one of the most famous one here, well, this is the most famous Volterra equation. Well, by the way, there are two different versions of them. Well, up to change of variables, you can interchange u and u1, and then u minus 1u. So here it doesn't matter what order you write, but the order so this is one of them. Well, other examples, there are two different versions of the modified Volterra equation. Yeah, by the way, here alpha is a scalar parameter. So if you wish, alpha is alpha times identity matrix. So it's possible to study equations with non-abelian parameters, but we will assume that all the parameters in the equations will be scalar. So this is the second version of the Volterra equation now. Two different versions, additive and multiplicative version of Bogoliansky equation, and today I will show some other versions of the Bogoliansky type equations. I'm not sure who first wrote all these, so these equations definitely appear in the Bogoliansky paper of 1990s, but I believe it was known before. So I think Sasha may answer this question, historical question, who was first here. Well, the aim the aim of this study is well, first of all, to solve the following problem. Given an equation, can we establish if it is integrable or not? So what are the necessary conditions of integrability? And secondly, if we derive such necessary integrability conditions, then can we obtain classification results? Well, I will mostly speak about non-abelian equations, and then in the end, if I have a few minutes, I will also show abelianization of these, and you will see that in the abelian case, there are other equations appear, and some equations disappear. Right, so a bit of setup. So as I said before, we can consider our dynamical variables living in some associative free algebra. So let A be an associative algebra generated by variables un and nz and an identity. And all parameters will be scalar. So yeah, we will denote by alpha times E will be just we will denote just by alpha, simply. Well, shift automorphisms. So we have shift operator, which sends un to un plus 1, keeps all the constants the same. So S of E is E. And the action of shift on, well, any element of our algebra is just shifting all the arguments by 1. Next thing which we will need is the natural grading on the algebra A. Natural in the sense of degrees of nonlinearity. So A, it can be written as a direct sum of subspaces AP, where AP consists of P-U's. So U0 constants, A0 constants, A1 linear terms, A2 quadratic, and so on. So this is the natural grading by degree of nonlinearity. Well, by pk, we will denote a projection from A to ak, and well, every element can be uniquely written as a sum of fk, where fk is a projection on ak subspace. So clear. Well, next thing we will need is a notion of derivation. So derivation is a linear map satisfying Leibniz rule, and in the case of abelian algebras, non-abelian free algebras, every derivation is completely determined by its action on generators UK. And probably the most important for us class of derivations is so-called evolutionary derivations. So evolutionary derivation is a derivation which commutes with the shift operator. And therefore, evolutionary derivation is defined just by one element, by the action on U. So if we know the action of U, we know the action on UN, we just shift UN by n times. So A we shall call the characteristic of an evolutionary derivation. Well, Linear combination of evolutionary derivations is again an evolutionary derivation. Commutator of evolutionary derivations is an evolutionary derivation again. In fact, the evolutionary derivation for, well, all derivations form Lie algebra, but evolutionary derivations form a subalgebra of evolutionary derivations. Well, next thing, that's the gradient which I will need, is the operator algebra on A. So by LA, we will denote an operator of left multiplication by an element A. By RA, we will denote the operator of the right multiplication. Left and right multiplications obviously commute, and then product of multiplication operators. Well, these are obvious rules. Then by M, we will denote an algebra of operators left multiplication by A, right multiplication by B, AB elements of A. And since A is graded, naturally graded, we have this algebra inherits the same natural grading. So subspace MPQ consists of operators LA RB, where A is an AP, B is in AQ. So on the left, we multiply by element of degree P. On the right, we multiply by an element of degree Q. Well, difference operators. So by difference operator, we will understand a finite expression of these forms. S is a shift. Coefficients leave in operator algebra. Also, each element here is some left multiplication, some right multiplication times shift. Shift we can always bring to the right. And finally, formal series. Now, infinite sums. So sum over grading and sum over power. So the shift operator, we will consider only negative direction. So I, let's equal to some fixed n in Z, and local formal series have coefficients in MPQ. Great. Okay. One last thing which I will need before I will define well, before we define differential difference equations on associative algebras. So Frechet derivative. Frechet derivative, Zhenya already considered it today. Linearization operator. So we linearize each UP which we replace by UP plus epsilon SP acting on A, and then take yes, epsilon equals to 0 is forgotten. Sorry, a typo. Epsilon equals and set epsilon and keep terms only up to order epsilon.
Derivative in direction A.
In direction A, yes. Well, so this is an example. So this is the right-hand side of the Volterra chain. So first u to power u0, so s to power 0 multiplication of on the right by u1, then multiplication by u on the left shift, minus multiplication by u on the right shift inverse, minus multiplication by u inverse on the left. Well, having so Frechet derivative allows us to introduce a Lie bracket. In fact, Lie bracket on A we can introduce in two different ways, equivalent ways. Either so a Lie bracket of elements A, B, either defined as derivative of B in direction of A minus derivative of A in direction of B, or Frechet derivative of B on A minus A star B. This is the same equivalent definition. Good. So finally, because of these, because of the natural grading of A, our Lie algebra is also naturally graded. So AM commutator is in AN plus M1. And we can now define the notion of evolutionary differential-difference equation on the free associative algebra. So for every element f, every element f corresponds an evolutionary derivation df, and by an equation we will understand ut equals f. Now understanding that every generator of our algebra A depends on additional parameter t. Well, next we can define the notion of a symmetry. So a symmetry of our equation is another element g of g from A such that f and g commute. So Lie bracket of f and g 0. And well, the order of the equation, well, actually is defined by the order of the Fréchet derivative operator. If G is a symmetry of our evolutionary equation, then derivations df and dg commute. So this is the same as commutativity of f and g elements, and it is a common way to write every symmetry in the form of an evolutionary equation, again assuming that every generator again depends on additional parameter tau. So u tau equals g is a symmetry defined by derivation dj. And here is an example. So the very first symmetry of the Volterra equation. So this is the non-abelian Volterra equation, and its first symmetry of order -2 is given by this expression. So now by the order we will understand a pair on the left, the most negative shift, on the right, the most positive shift. So in fact, the Volterra equation possesses infinitely many symmetries of all orders -n for every natural n. Well, perhaps I should give another example here. So I will not write with symmetry, but I will just mention u1, u2 -2, u-1, u. So this is a multiplicative non-abelian Bogolinsky equation of order -2. Its next symmetry will be of order -4, 4. And this equation, in fact, possesses symmetries of all orders -2n to n and any natural number. Right. Well, any linear combination of symmetries is again a symmetry, and in fact, well, Lie bracket of symmetries is again a symmetry. So symmetries form a Lie algebra, and now we are ready to define the integrability. So we shall call our non-abelian equation integrable if its Lie algebra of symmetries is infinite dimension. In other words, the Lie algebra of symmetries possesses symmetries of arbitrary high order. So for whatever large n we choose, there exists a symmetry of order equal to or larger than that order. Good. Now a bit more of a symmetry structure. We have a natural grading by degrees of nonlinearity on our algebra A, and therefore it is convenient to seek symmetries approximately. So we have a grading in degrees of nonlinearity, so we may consider the compatibility condition fg equals to 0. We can split it by degrees of nonlinearity. So fg equals to 0 is in fact equivalent to m plus n minus 1 relations of the form here, where n and m are the highest degrees of the equation in its symmetry. we shall, from the beginning, assume that we consider equations which do contain the linear term. So F1 here, so linear term, is non-zero. And we shall also assume that F0 is zero, so there is no constant term. If F1 is zero, then the symmetry also must start with a linear term, which is easy to show. And then, because of this, these relations can be formally resolved for every given f. So if f is given, we can formally one by one find formal expressions for all the G2, G3, etc., given by G1. This is because we can formally invert add F1, and this can be done in what is called the symbolic representation. So I will not talk about the symbolic representation. All what I will do is just give you a hint what is actually going on. So we can represent every element of AP or every element of our A by symbol. So constants we will represent by constants, and every element of degree P, UI1, UI2, etc., UIN, we will represent by symbol. So instead of writing I1, I2, etc., n, we write xi1 to power I1, xi2 to power I2, etc., xin to power IN. So this is an element of degree n. And well, here is an example. So UK goes to U xi1 to power k. U1, U minus 1 has a symbol xi1, xi2 minus 1, and so on. And generally, symbol of an element of degree n is a Laurent polynomial in n variables xi1, etc., xin. And the shift operator in this symbolic space acts by multiplication, so multiplication by a product of all variables. And then, as I said, so let me go back. These relations can be formally, so if f is known, can be formally resolved in terms of elements of G. And these are explicit expressions of this. I will just give a snapshot of this. So if our equation has a symbolic representation, this is a symbolic representation of the linear term, quadratic term, cubic term, then A2, A3, etc., can be found uniquely in terms of f and this omega via formula like this. So for A2, this is the explicit formula, and then there are recurrent relations. So A3 is first term is here plus something what depends rationally on the previous terms. So these are recurrent relations. And now you see, so we for every equation, we formally resolved the commutator relation. So we are inverted add F1, if you wish. However, if these are coefficients of the symbol of the symmetry, this must be Laurent polynomials in their variables, not just rational expressions. And therefore, you can see that these, so first of all, these little letters are given by the equation, but the other parameter we have is the linear part of the symmetry. So we shall call the linear part admissible if all these coefficients are Laurent polynomials, and therefore the algebra of our symmetries is completely parameterized by a vector space of these admissible linear parts. So if we know them, we know the whole symmetry structure. And if our equation is integrable, then this vector space is infinite dimensional. However, the trouble is how to find, for a given equation, how to find this vector space. So as I said, for Volterra equation, it can, for Volterra, well, let me show you the next example, how it works actually. So this is an example of the Volterra equation. So ut is u1 minus u minus 1 u. This equation does not have a linear term, as you see. So there is no term in u1. However, we can introduce it simply by shift. So we can shift u OUI by 1. So we get U1 minus U minus 1. So this is the term from A1. And this is already A2. So this is, then the symbol of linear term is xi1 minus xi1 inverse. This is the symbol of the quadratic part. And then from Wolff's formula, you can see that if we choose omega capital to be xi1 squared minus xi1 inverse squared, then A2 is this Laurent polynomial, A3 is this, and then in fact, in this case, it will just truncate. So we will have A2 and A3 and no further terms. AS equals to 0. And one can show for the Volterra equation, the vector space of admissible linear terms is spanned by elements xi to power k minus xi minus to power minus k, where k is an arbitrary natural number. Well, the vector space of admissible linear terms for the Bogolinsky equation, for instance, is much more complicated. So it is spanned by elements of the form 1 plus xi1 plus xi1 squared to power k minus 1 plus xi1 inverse plus xi1 inverse squared to power k. So that's the element, that's the vector space of the admissible terms. Well, next thing which I want to say is, well, as I said, that it is very difficult to find the vector space of the admissible linear terms. If we know this vector space, we can, for a given class, we can in fact pick an element from this vector space and use Wolff's formulae as a classification test. However, well, it's possible to derive conditions without that knowledge. So we may have conditions without knowledge of the vector space of the admissible linear terms, and this boils down to the following classical problem. We know that if we have a formal series, formal differential series dx to power n plus some differential polynomial dx to power n minus 1 plus etc., and then we can extract a root, nth root of this formal series, and coefficients. So if the coefficients of the original formal series are differential polynomials, then coefficients of the root will be also differential polynomials. The same problem in the case of difference formal series does not have this nice solution. So in fact, for a generic formal series, well, let's say s to power n, and then this is the only linear term, and then all the rest of s will be multiplied by some left and right multiplications. So if we want to solve the equation a equals to b to power n, so b to power n equals a, extract root of order n, then generally there is no local formal series b satisfying this equation. And even more, it exists only if a is already nth power of some local series. However, this root, so if this root can be formally computed, and it actually belongs to an extended algebra of formal series. An extension is given by the following operators. So if we now define by theta k these, so 1 plus s to power squared plus etc. plus s to power k inverse. So if I allow the action of operators of this form on elements of our A, then the root, coefficients of the root, will belong to this extension. So the extension is, well, this is the construction of the extension. So M0 is our original space of left and right multiplications by local formal elements, and then M1 we allow action of theta once, M2 we allow action of theta twice, and so on. Well, I write here s goes to infinity. So in fact, so this is not a limit. So we usually say that an element belongs to an extension if there exists sufficiently large s such that an element belongs to the extension. And then we shall call an algebra of formal series with coefficients in this extended algebra of left-right multiplication, an algebra of quasi-local formal series. And then the root, we can extract the root. So if A is a local formal series, s to power m plus something nonlinear, then there exists a unique B, quasi-local B, such that b to power n equals to me. Now, working with this extension is actually quite difficult. That's why the symbolic representation is needed. So working with this extension explicitly in this in the standard form is not an easy problem. So let me now formulate the main theorem. So first of all, the definition, a formal series lambda. So linear, the first term, phi of s is some Laram polynomial on S. And then nonlinear terms is called the local formal, is called the formal recursion operator for our equation. If it does satisfy the equation, lambda t is f star lambda minus lambda f star. By t, here we understand the derivation with respect to t, our equation of coefficients of lambda. And then the following theorem, that's the main theorem here, that if our differential equations with non-zero linear part and zero constant part possesses an infinite dimensional algebra of symmetries, then there exists a quasi-local formal recursion operator starting with order 1. And this is now the necessary integrability conditions. So what is being done is coefficients of this formal series solving this equation can be found explicitly formally in terms of symbols of our equation f star. And then all what we need to do is verify that these coefficients belong to the appropriate algebraic extension. Right, so let me now just give you a hint why we need this root extraction. So that's the idea of the proof of this theorem. So let's take a symmetry of very large order. So it depends on un, and n is much bigger than the order of our equation. Then the linear part of this symmetry, well, we'll assume that linear part, well, sorry, here should be n capital, not n small. That's important. Then the condition of commutativity implies this relation between G star and F star, and the left-hand side is, or rather, better say, the right-hand side is of order n, where the left-hand side is of order n capital, much larger than n small. So n minus n coefficients of G can be formally found just from this part equals to 0. So therefore, formal recursion operator is approximately G star root of order 1 over n. So this is why we need this root extraction, and this is why we need this quasi-locality. And now let me show you the, well, I have about
7 minutes, I think.
7 minutes, yes. Let me now show you the classification results. So we classify skew-symmetric quasi-linear equations of orders 1, 2, and 3. So skew-symmetric means that, well, we need, let's introduce this operator, which changes n to minus n and transposes elements. So it's involution and transposition. Quasi-linearity means that it depends on highest shifts linearly. now we need the condition that there is non-zero linear part, and there is no constant term, which we already eliminated in the very beginning. And finally, for equations of order greater than 1, no lower order symmetries. So first theorem, equations of order -1, 1. Every equation of order -1, 1 can be obtained by shift and rescaling from these two. This is linear equation Volterra and modified Volterra. And this is the second modified Volterra. Now alpha here is, as I said, a scalar parameter, alpha times identity. All right, now the list of equations of order -2, 2 and -3, 3 split into two subclasses: equations of Volterra type and equations of Bogolinsky type. Now equations of order -2, 2, Volterra type. So again, so now the first equation, so these first two actually these are what is called stretched equations of order 1. So we can replace ui by u2i. For equation of order 1, we obtain equation of order 2. So these are trivial from the previous list. The rest are not. And then so this is the complete list of Volterra type equations. And second list is list of Bogolinsky type equations. So the first one is the additive Bogolinsky equation, multiplicative Bogolinsky equation. And then they appear, like in the case of modified KdV, other versions. So here commutator is usual commutator, u1, u minus u1. So it's not a Lie bracket. So and then subsequent list. And then now the list of equations of order 3 minus 3. Again, a pair of stretched Volterra equations, and then another 5. And Bogolinsky type. So again, usual additive Bogolinsky, usual additive, usual multiplicative Bogolinsky, and yeah, let me draw your attention to equation 4. So it contains a parameter. So in the abelian case, so if all variables commute, this is it reduces to one of the standard Bogolinsky equations. However, so I found this equation in the original paper of Bogolinsky in 1993 without parameter alpha. So somehow, so he wrote a lax representation for this guy, but without parameter alpha. Alpha is not removable. Alpha is not removable from this list. And finally, one more. So this is the last one. So these are equations of order -1, 1, -2, 2, -3, 3. Do I have 2 minutes? All right. So let me show you now similar classification. So I skip all the setup for abelian equations. So let me now show you classification of abelian results. Well, I have 2 minutes, so 1 minute I will spend on previous results. First of all, 1983, the famous classification of Ravili-Emilov of Volterra type equations of order -1, 1. This theorem, this classification theorem, used the fact that an equation of -1, 1, he requested the existence of symmetry of order -2, 2. So he did not have the notion of a formal recursion operator. Next classification, which was done, well, actually it was a sequence of classifications, equations of the form of Toda type. Well, Toda, relativistic Toda, Ablovitz-Ladik, etc. This is Adler, Shabbat, Yemilov, and company in 1990s. Then there was a big gap, and then 2017-18 classification of second order quasi-linear equations of order -2, done by Yemilov, Garifulin, and Deche-Levy. However, they again did not have a notion of a formal recursion operator. All what they requested is the existence of a symmetry of -4,4. Meanwhile, Seva Adler proved an alternative theorem of existence of formal recursion operator. I don't have time to show this, but there exists an alternative version of formal recursion operator in the abelian case. Not in the non-abelian case, it doesn't, but in the abelian case, it does exist. So this is the classification of quasi-linear, skew-symmetric, third order -3 equations. So they split now in 3 classes. Volterra type. So these are abelian Volterra type equations, and now you see rational expressions appeared. They don't survive in the non-abelian case. In non-abelian case, surprisingly, all the equations are polynomial. So these are all the abelian Volterra type equations of -3,3. Now, Bogoliansky type. This list is shorter. Again, well, this list does contain abelian versions of all the equations which I just showed in the non-abelian case, plus additional ones. And finally, there is a third class, equations of what is called Savada-Katera type. So these are, well, I didn't explain this, but these 3 classes differ by the vector spaces of admissible linear terms. Volterra type clear, Bogoliansky type I have shown, and these ones are linear terms do contain an arbitrary parameter. And finally, yeah, probably the last one which I showed, the last equation is definitely new. This is the last one which does this is the Savada-Katera type, and this one, as you see, well, it doesn't survive in non-abelian case, but yes, up to the best of our knowledge, it's new. Right. I think my time is up.